All right, welcome to Monday again. I'm going to make a video because this is a brand new topic. We're going to edge out of stoichiometry for a little while, but very soon we're gonna get back into it. And so don't let those ideas go out of your head for stoichiometry, if they haven't already. Uh, I want to talk today about different types of um, chemical reactions that include what's called a precipitate. We are going to focus on ionic compounds. Now, ionic compounds we already know about, and we're going to spend certainly till the end of the month talking about ionic compounds and different types of reactions associated with ionic compounds. We've already talked about a few of them. We've talked about double replacement reactions, and they're pretty easy. And we said, for example, in a double replacement reaction, we'd have something like this. We'd have KNO3 plus, wrong ions here. We'd have KCl and say, for example, something like silver nitrate, and we would have a double replacement. And the double replacement, remember what that was?
They switch.
Yeah, they switch partners. So you're going to get exactly. Great. See, not bad for a Monday. But if you were to do this reaction, you would see that this one came out like a solid, very much like I showed you the yellow lead iodide that I had up here on the desk. Now, this type of a reaction is called a precipitation reaction. A precipitation reaction. And this solid that we get is called a precipitate. Okay, so the reaction is a precipitation reaction, and the solid that you get is a precipitate. So the question becomes, well, what happens to the other ions? And how can we represent this chemical reaction to show the net chemical reaction, which we call the net ionic equation? And also, how do we know if something's going to form a precipitate? Well, we have a set of rules to explain that, and they're not too difficult. And we have a beautiful chart on the wall there called the solubility table. I want to show you something now. About ionic compounds in solution. So first of all, if I take an ionic compound that dissolves, let's go back to KNO3. If I mix that up in water, it'll form an aqueous solution. But what does that really mean? It means, I put it in some H2O, you're going to form potassium ions floating around plus nitrate ions floating around. Okay? This is called an ionic dissociation. Okay? If this just sits in the jar, you just have potassium nitrate as a solid. But as soon as we mix it up, there is no more, quote, potassium nitrate as a solid in there. It is potassium ions and a soup also containing nitrate ions. So this is an ionic equation. It just shows you what separates. Now, some interesting things about ionic compounds. Once I dissolve this, look at these two particles. They have electrical charges on them. The potassium has a positive charge, the nitrate has a negative charge. So ionic solutions they conduct electricity. Because anytime you can have a flow of charged particles, you create a current. current is a flow of charged particles. Let's put this on pause, and I want to take you back to the lab and show you a demonstration. It's one of my favorites. Okay, so we just saw the famous light bulb experiment, light bulb demonstration, where we take a light bulb and put it in deionized water. Of course, the circuit's broken and the light bulb doesn't light up. But then we put some potassium chloride in the water, and we saw that the light bulb not only lit up, but the more potassium chloride, the higher, well, this is potassium nitrate, but the higher the concentration of the ions, the brighter the bulb would get. So these ionic compounds sometimes are called electrolytes for that very reason. For this idea that these ions are produced and they have charged ions. Okay, well, let's take a look at that first reaction that I showed you. It looked like this: KNO3. Oh, no, I did it again. KCl, aqueous, plus AgNO3, silver nitrate. I don't need a parenthesis there. Aqueous, to give KNO3 aqueous. Aqueous means it's still dissolved, plus Ag, silver chloride, and that was a solid. And that's going to be one of these things that we do in lab, is to examine this very chemical reaction. So, first of all, how do I know which ones are going to be aqueous and which ones are going to be solids? That's the question that we're going to answer today. So if you were to take a look, let me see here. Well, we talk about it in your book a little bit on page 221, but I'm going to go into a little bit more depth than in your book on page 221. I'm going to print you off a solubility chart, but for the time being, look up there on the wall, if you can, and what I want you to do is find where the different ions intersect. Let me go over and show you. Okay, sorry about the video being a little disjointed. I'm running back and forth to the solubility chart on the wall. But you will have that solubility chart. I'll post one on the class page so you'll have a link to it. Now, this is called the overall chemical reaction. And we just saw, if you look on that matrix, basically, where K and Cl meet up, it says soluble. That means aqueous. So we can write it this way. K plus Cl minus aqueous. So that's just what I showed you before, those things breaking up into their ions. And on over here, we're going to have some silver ions, aqueous, and some nitrate ions, aqueous. So let's say I just have one test tube and it has a solution of potassium chloride in it. It's going to look like water. It's going to be just perfectly dissolved. And let's say I have another test tube of silver nitrate. Okay, hold it up. Oh, it looks like water. I'm going to mix these two together. One of the things is going to be a salt, and we can look, like I said, on the chart where silver and chloride are, where they meet up there on that matrix. And you would see insoluble. And insoluble, of course, means a solid. And this would still remain in solution as KNO3. So let me erase these little boxes here. I was just trying to show you that they're two separate containers, and before we mix them, everything's a big mess of ions in each. After we mix them, though, you're going to get K plus aqueous plus NO3 aqueous plus AgCl solid. Okay. So this first equation is just called the overall reaction. That's just what we're doing. This is called the total ionic equation. And the only difference is everything that's aqueous we break up into ions. And finally, and the goal we're trying to get to is to look at something called the net ionic equation. And the net ionic equation is just the equation that represents the chemical reaction. Now, one of the things that I said to recognize a chemical reaction taking place is the formation of a solid. We talked about that weeks ago. So, just like in algebra, if we cancel out like terms on both sides of the reaction, we'll look at potassium with a plus, aqueous is on that side. Potassium with an aqueous is on that side. And nitrate and nitrate, they would sort of cancel out. It doesn't mean they've disappeared. It just means they're still floating around in that ion soup. But look what happens. So if I have silver and chloride, well, those two are going to get together. And on this side, it's in a whole different form. It's a solid. So AgCl is a solid. So this little reaction here that just shows the two things that react to form a solid, this is called the net ionic equation. So that's what the goal is, to be able to use your solubility chart and predict products for an equation. So that's what we're going to do, and we'll spend some time doing that.